added is I want to motivate it and give you some background. So let's start with a very simple question you might not think about. How often do computers make mistakes? So let's think about the following simple math problem. 10 to the 48th plus 914 minus 10 to the 48th plus 10 to the 32 plus 615 minus 10 to the 32. And since you know that you can rearrange terms, the 10 to the 48s and the 10 to the 32s cancel each other out, so you're going to get 914 plus 615, which is 1529. But what happens if we ask this question to a computer as stated? So let's type that formula into Excel. You'll see you get an answer of 0. Got that wrong. What did I do wrong? Maybe it's just Excel, maybe you don't trust that product as much. Let's go try something else. Here's Octave. And lo and behold, Octave gave us the same answer of 0. In fact, almost every program you ask will give you an answer for 0, of 0 for this. We have to ask why. So to do this, we're going to look at how numbers are represented in errors, and then we'll come back to how this is actually related to linear algebra. So the first thing we want to look at when we consider how we represent numbers is we have to store them in a computer. We have finite precision. We're going to represent them. So we're going to talk about this idea of normalized floating point representation, and we'll spend a little bit of time on that. This isn't in the book, but we'll go into that in some level of detail. In other courses in your computer science degrees, you're going into those in even more details. But even if it wasn't for that, there's some other forms of errors. We have human errors. It's caused by inaccurate measurements of data or inaccurate representation. So if I wanted to have those numbers, for example, be lengths, some of them might be lengths I measured with a ruler, and I might have an error. I can have truncation errors when whatever mathematics I need to do forces me to represent it with a fixed number of digits. I can either truncate it or I can round off those errors depending on which of two techniques, and we'll look at those a little bit as well. We can look at how they affect things during arithmetic operations. So when I go to do addition and subtraction, how does that round off error affect the calculations? Multiplication is similar. We're not going to go into that here. Division is actually at much more significant impact in terms of that than multiplication, but we won't go into it here. It's pretty important because it is common. And roots and powers also give this, but again, less common. But I wanted to give you a feel for a couple of these, so we'll start with addition and subtraction just so you can sort of see them. So why do we really want to worry about round-off errors? It's just some made-up example. Well, it turns out that there have been lots of physical things, North Sea oil rig, Vancouver Stock Exchange, a rocket that blew up, Patriot missiles that ended up not tracking their target because of accumulated round-off error, a couple of bridge collapses. All of these can be traced back to round-off errors, and many, many more financial examples where people have had these kinds of problems. And so these are very real problems. You need to be somewhat aware of them in terms of how you're going to use the computer. So let's start talking about the difference between how we represent numbers in the computer and our real number system. So in our real number system, we can write things in decimal notation. They can be infinite. We can have as many digits as we want. It includes all positive and negative numbers, fractions, irrational numbers. Lots of things go on in the real number system. But in a computer, we have to have a fixed representation. So actually, if we think of our real number line up here, and we think about our floating point numbers are going to use one number to represent many, many real numbers. And that's because all of these real numbers will have the same representation. Think of it as if I'm only allowed to have 10 digits and I change the 11th digit, a bunch of numbers will be about the same. And so our numbers, floating point numbers, are going to be a much sparser representation of real numbers. You'll also notice something else about this drawing. Do you notice that these cones, some of these cones are much bigger than other cones? And so we're going to have this problem right around here where different resolutions will have different errors. So let's talk a little bit about how to actually do this representation and make it a little bit more formal. So if we think of a t-digit base B floating point number, we're going to represent that as either plus or minus, so we have a sign, t digits, d1, d2, d3, up to dt, t digits, b, which is our base, raised to the power e. In our terminology, we're going to call d1 through dt the mantissa, b is the base of the number system, and e is the exponent. And in most computers, of course, we don't represent b. We're going to use binary, so b will be 2, and we don't need to store it in the computer, and we're going to just represent the digits in the mantissa and the exponent plus the sign. The exponent is generally an integer between two fixed integer bounds. some say negative bound E minus E1 and E2. Many computers will actually represent them in a bias form so that they're always positive, but it's like you add 128 to the number, and now it goes between 0 and 255. So you can have effectively negative numbers by subtraction. Now, when we go to represent these in computers, a couple other things we're going to want to worry about. So we have what we call normalized representation. We're going to represent base B, the length of the mantissa, how many digits we have, and then bounds. This gives us our representation. But we also have to worry about what do we do when we go to put a number into the computer. So we have two choices. We can chop or truncate the number. So if I have more than t digits and I want to reduce it to t digits, everything past the tth digit is discarded. So if I have t equals 5 and I'm working in decimal and I had the number 2.58738928874, the result would be 25873. We chop it off here. And now you probably all learned back in high school about the slightly better technique called rounding. A number that is rounded when you sort of round, and there's a couple different rounding techniques, but we try and approximate it with minimum error. So in this case, because it was 3.8, we'd actually make it 7.4, so we'd round the 3 up. In decimal, the sort of rule of thumb was you take the digit after the one you're truncating and say, is it greater than, is it 0.5 or greater, taking all the remaining digits. If it is, round up, otherwise round down. And you can round high, round low. There's a couple of variations. But we don't always actually have that choice of rounding versus chopping. Rounding, if we have to do it, means we have to keep extra digits lying around so we can decide what the final answer is, and that can be complicated when you have a computer and you have a fixed set of registers to represent everything. So computers often have a little bit of both rounding and chopping, and then in terms of chopping, it's also the possibility that whoever entered the data into your computer, it came from the outside world when it came in, could have had that error introduced by chopping at the time. So in a computer, our computational steps must be performed within our computer, so bounded arithmetic, in the sense of both finite precision and finite range. So by finite precision we mean, and this is a term you should know, could be on the midterm or final, computation must be done in the presence of rounding and truncation error, and by finite range we mean that it has to lie within the range you can compute. So those are two important terms, finite precision, finite range. So coming back to our floating point representation, we're going to go through a little bit more. So I can think of my number x as either being plus or minus b raised to the power e times a fraction of points d1, d2, dt, whatever, up to dt, where di is between 0 and b minus 1, where b's our base. So again, in binary, they'd be zeros or ones. Which we can also think of as just writing it out as a fraction, plus or minus b to the power e, d1 divided by b, plus d2 divided by b squared, and so on up to dt divided by bt. And so this gives us another way of looking at it. Now it turns out that since I'm going to do this, I actually have a little bit of ambiguity. If I were to add a 0 in front of D1 and shift everybody over, then I could just change E and change my representation. So in practice, we actually require that D1 is the number 1, and then we call it normalized. And the advantage of that, and almost all computers today use this representation, is if D1 is going to be 1, then I don't even need to store it because I know it's always a 1. And then I can save one extra bit and get T plus 1 even though I only have T bits of storage. And that number would be called a normalized floating point representation. Sometimes computers can represent denormalized numbers between 0 and the smallest normalized number, and they're called subnormal, and that's a possibility, and it's a question of whether a computer is going to allow you to represent that. And we'll see one of the things that happens with that in just a second. So to look at it physically in my computer, I might say I have, for example, two 16-bit words as my representation, and then I have a 23-bit mantissa, 8 bits of exponent and a sign bit, and this is a pretty common single precision floating point number, 23 bits of mantissa, 8 bits of exponent. Now one of the things that happens, if you recall I showed you those different spacings, is we in fact have another issue which is called the hole at 0. Once I get that denormalized number, there's nothing between it and 0 in terms of the normalized number, sorry, between the smallest normalized number, either positive or negative, and 0, there's a gap. Here I have some spacing with numbers, and I'll show you that gap in this drawing here. So the numbers are densely spaced, they get more dense, and then all of a sudden, boom, there's a jump to 0. By allowing denormalized floating point numbers, you can get a few points in here, but it still ends up with a very sparse spacing in terms of where that gap is going to be. So not only do we have to worry about this varying of precision depending on where you are in the number line, we also have this issue right around zero called the whole of zero that we might have to worry about. Now, all of this it turns out to be way more important than it might sound like it is, because you have to remember that when we represent decimal numbers, even correctly rounded in a base other than 10, for example, in base 2 or base 16, they're not going to have an exact representation. So if I take the smallest American denomination of a penny, $0.01, turns out that does not have an exact representation in your computer. It will always have an error. There's no way to exactly represent it. You can round it, you can truncate it, but it's never exactly 0.01. And that means when I start doing operations with lots of money, where pennies are what I'm talking about, I have to worry a lot about what will happen with that round-off error. We have to consider truncation errors and how they propagate. So if you had this 6-digit number, you truncate it, and then do proper rounding, those two are very different. But if I do a lot of calculations, that truncation error can accumulate over time. For example, in that Patriot missile example I mentioned in terms of round-off error, it actually had to accumulate round-off errors for weeks before the error would actually mean the missile would miss. But you want to keep your missiles on standby all the time, so you have to balance those two out. So going back to sort of see that normal and sort of normalized form. So just to make a very real example, here's a complete but relatively small number system. My base is going to be 2. I'm going to be allowed to have 2 digits. My exponents go from -2 to +2. Okay, that means I can represent numbers like 0.10 in binary is the number 1/2, 0.11 is 3/4, 0.01 is 1/4, and so on. And I can represent them again as a power, 2 to the -2 times 1/2, times 2 to the 2 times 3/4, right? And so on. And this will give me up to the number 3 is largest number I can represent here. So, but I can't have a denormalized or subnormal form where I have 2 to the -2 times 1/4. Right? Things were supposed to be multiplied by powers, but here I'm multiplying it by a subpower, so I'm going to get 1/16. In this representation, the complete set of non-negative normalized numbers, so properly normalized numbers, are 0, 1/8, 3/16, 1/4, 3/8, up to 3. These are all the numbers you can represent in this very limited system. And we can sort of draw them out here. We'll see 1, 2, 3, half, 1/4, whatever. This dotted line here is actually showing you the denormalized number that we can also represent in this, still leaving a little bit of a gap towards 0. In this representation, 1/2 times b to the 1 minus t is 1/4, and that is our relative machine precision. That's when we represent numbers, they're going to round up or down 1/4. Now, we have another possibility, especially in a small number system like the one I just showed, which is when the result is larger than the largest number you can represent in the computer system, which is basically once your exponent gets to be too large, then you can't represent it. And almost all computers will give you some sort of an error when this happens. Now you have to be careful because the computer will gladly let you do computations using the numbers that have overflowed. Normally that number is called not a number, NaN. And you can then add it to another number, and the result of NaN plus 7 is NaN. Gives you weird results, and you have to propagate for them, so you have to check for that. But most computers will give you some kind of error. Another one, maybe a little bit more insidious, is what's called underflow. Underflow is when the result of a computation is smaller than the smallest quantity the computer can store, not in an absolute value, in an absolute value sense, not in a negative sense. So now I'll have a number that is, say, 10 to the -4 in my previous number system, where I had 10 to the -2, and the computer can't deal with that. Some computers don't actually see this as a 0 and just set the number to 0. Other computers have modes where you can tell them to let you know if there's an underflow, but otherwise they'll gladly just give it to you as 0. Okay, so machine constants and how to deal with these, there's a whole bunch of rules. This is pretty complicated. The amount of round-off to pairs in the floating point format of a computer, before errors can be corrected, you have to identify them and play with those constants. There is a standard called IEEE 754 for binary floating point arithmetic, which actually, if we go look back over the range of history of computers, wasn't at all the most precise. In fact, it matches exactly the IBM PC standard, and the Intel chips that came out to support that ended up driving the IEEE standard. You'll see this gives you pretty good representations. So you have your total number of bits are 24 bits for single precision and 53 for double precision. Again, this is using the implied 1, so they get an extra bit out of it. Your upper and lower exponents, so for single precision you get minus 126 or plus 128, so they're not quite symmetric in terms of the smallest and largest exponents. Double precision gives you more than that. And your epsilon, your machine precision, is about 6 times 10 to the minus 8 for single precision and 1 times 10 to the minus 16th for double precision. It gives you pretty good precision. There have been many computers made with better and some with much worse precision. But IEEE has become sort of the standard. You have to be, one word I do want to point out is you want to be a little bit careful. If you're using a GPU, like an NVIDIA or AMD GPU for calculations, many of them do not follow the IEEE standard because it turns out to be a little bit more expensive. So you'll get something that's similar but not exactly the same result across that. The reason for introducing IEEE standard arithmetic is so that results on different computers would give you the same results. So it specifies the floating point, some results of basic operations. It has a bunch of rounding modes. It defines values of signed zeros and infinity and deals with the issues of not a number. It has formalizations for floating point exceptions and how you handle them, and conversion between formats. And as I said, most modern computers use IEEE arithmetic, but you might find your phones don't. You might find your GPUs don't. So you got to be a little careful as you try and generalize across many platforms. In addition to the single and double precision that I already mentioned briefly for IEEE, there's an extended precision, which most machines support. And this is actually a sort of a more interesting mode. One, because it gives you a much larger range for your exponents, gives you more an increased precision. And for most of them, this has the negative side effect that your computer is only going to store the 64-bit numbers. By the time you add 53 and 11 for your exponent, in your sign, you see you have 64% bit double precision numbers. Extended arithmetic, because it actually is using 80 bits, happens only inside the registers of the arithmetic processing unit, and so you can never get these data in or out. But if I do a long sequence of calculations inside, I can keep them inside the registers. So even though we use IEEE formats, if I change and I mix double precision and single across machines, I'll get different answers. If I mix double or double plus extended, I can get different answers. So order of computations will still matter a little bit. We'll talk about this idea of what I call the machine epsilon. And it's the smallest amount of round-off error such that when I add it to a number, the machine will still represent it. It's easily represented by asking the question, when I do a floating point operation to 1 plus epsilon, if epsilon is greater than machine precision, then I'll get an answer that's greater than 1. If epsilon is small, the smallest epsilon for which this is true will then give us the machine precision. So in fact, we can use that to estimate the machine precision by writing a little bit of code. Here's a very simple bit of C code that is basically going to just start off printing out a value for epsilon. Epsilon is going to start at 1. It's going to then add 1 plus the machine epsilon divided by 2 and decide if it's equal to 1. If it is, it's going to stop. Otherwise, it's going to go up and it's going to divide machine precision by 2. So it's going to just keep dividing until it answers this question. So if I run this on my laptop and I put in single precision floating point on my Mac, I'm going to get 1 and then 0.5. I'm just going to keep iterating until I get a machine epsilon of 2.348. Whatever. So this code is from Wikipedia. You can easily find it. It's relatively straightforward stuff to do. And the part that's interesting here is we notice this is that when we get done, we're really asking the question, when is 1 plus a number equal 1? We're actually using the fact that that's the failure. That tells us the largest number says that 1 plus epsilon is equal to 1, tells us a machine's precision. Now, that's for a single computation. If I go to work with lots of computations, I have to be careful about how they propagate. So an optimistic value for performing arithmetic operations is roughly sort of on average square root of n times epsilon, where n is the result of n arithmetic operations. So some of them will round up, some will round down, but when you're going to do it all together, you're going to get roughly the square root of n times epsilon. It can actually be n epsilon, depending on the calculation types, or even much larger. For example, this is actually what led to the problem we started with. So if we go back to that we go back to the idea of adding in a number, right? If I have 4 decimal digits in base 10 arithmetic, and I take 10,000 plus 1 minus 10,000, I'm going to get 0. Or 10,000 plus 1 minus 10,000 equals 1 is what we should get. So we have an error here. In fact, this is what led to the error on that first slide. How do you get the computer to not be able to add correctly is you make it add really big numbers and really small numbers in a bad order. If you'd actually swap that around, you could make it in the right order. There might be a way of computing it. Okay, so that gives you a brief introduction to round-off error and numeric issues. And again, computers, by the time they have to add big numbers and small numbers, have a problem because it can't represent the big number and the small number all at the same time, leading to a sequence of operations that will have an error. So now let's head back into linear algebra land and see how this is going to affect us in linear algebra. So we're going to start with the idea of vector matrices and norms. We've actually already talked a little bit about them. But again, think of norms as providing what is the length of a vector or a matrix, what is the scale of the transformation. The simplest of these is the Euclidean vector, which is just the square root of the sum of the squares of the elements, which you can always get. So as a vector norm, that measures the magnitude and length of a vector. It's fundamental to lots of operations. It exists in as many dimensions, and as we said, square root of the sum of the squares of the elements is the Euclidean norm. It's often subscripted by putting these double bars, v, double bar, and the number 2, saying it's the 2 norm. And it's pretty common, but it's not the only norm. In fact, we have many other types of norms. So we can talk about the 1 norm, which is called the Manhattan or taxicab norm, which is the sum of the absolute values of each of the elements. We can talk about the infinity norm, which is double bars infinity, which is just the maximum element. We can talk about, in fact, for any value of p, the p norm, which is v, each element raised to the p power, the whole quantity raised to the 1 over p power. And so 2 is a special case of that. It turns out that 1 can be rewritten this way if you think about how you want to use absolute values as you approach 1, but you can have 3/2. Okay? We often also talk about it from a geometric point of view. So if we think of the 2 norm, it actually draws a circle. It's all the points at a unit distance in the 2 norm form a circle from the center point. In the 1 norm, it actually forms a diamond. It's all points whose sum of absolute values can be this. And the infinity norm is the square, everything who's within a maximum distance. And it turns out that all values of p lie between this diamond and the square. You just vary those positions. So there's lots of variations in those norms, but these 3 are by far the most common. Just to put them, we can compute numbers. So here's the vector 1, 0, minus 2. The 1 norm is 3, the 2 norm is the square root of 5, and the infinity norm is 2. And you can show that there's a relationship between these norms. The infinity norm is less than or equal to the 2 norm, which is less or equal to the 1 norm. In fact, the p norm is always between the other values of p. So p equals 3 would make it less than 2 and greater than infinity. So when we start looking at how we do calculations, if we're going to try and be given some calculations and we want to find for 10 or 100,000 point pairs and a 2 norm tolerance of t, we want to find point pairs that are closer than t. We actually have to then do the square root of the sum of the squares for each of those points, which turns out to be expensive. And the 2 norm takes more CPU clock cycles than other norms. The max norm turns out to allow for trivial rejection of lots of points. So in fact, you'll often mix these. Since you know the infinity norm is less than this, if you're going to want to say you're looking for points that are closer than a particular value, if the infinity norm is greater than t, then the 2 norm will also have to be greater than t. So we can reject a point pair. And the 2 norm, the infinity norm is much faster because I just take the max over all the points. So you just keep running down the vector saying, is anybody greater than where it needs to be? If it is, reject the point. If it's not, then you can do the processing to decide if it's the 2 norm is true or not. And you'll get for lots of points that will work. When you're dealing with trying to render tens of thousands or hundreds of thousands of triangles, it makes a big difference. So some basic properties of our norms. Our norms are always greater than or equal to 0. The norm is equal to 0 if and only if the vector is 0. If I multiply my vector by a scalar, I just get the absolute value of the scalar times the vector norm. And then they satisfy the triangle equality. The norm of v plus w is less or equal to the norm of v plus the norm of w. And these are true for all norms, part of what it means to be a norm. So we could actually go back and might be asked to do something like this on the exam, who knows. Show that the vector norm properties hold for the infinity norm. So if we know the infinity norm is the maximum over all the elements, property 1 and 2 are pretty easy. The maximum value is 0 if and only if the value is 0 for all values. So that makes it easy to show that it's greater than or equal to 0 and that it's equal to 0. For 3, we just multiply in. We want to take the max of the absolute value of c times vi. That's the absolute value of c times the max of vi, which gives us this. Triangle equality takes a little bit more work, but not much. We want to take the maximum of the sum of the absolute values. Well, then I just take the maximum of the absolute value of each of those. That's less than or equal. Notice here, this is up here we had all equals. Here we're looking at the triangle equality. We get less than or equal to the max of the sum of the absolute values, which is less than the max of each of them taken separately, which is less than the infinity norm, and so we can bound the infinity norm. Okay, so these are all been for vectors. What do we do for matrices? So to get some geometric insight, if we go back to our 2 by 2 matrix, which maps a unit circle into an action ellipse, consider A transpose A, the symmetric positive definite form of that, gives us real positive eigenvalues lambda, and then we can talk about the singular values equal to the square root of those. That gives us the major and minor axes. And it turns out this gives us a way of measuring matrices. And so if A is symmetric and positive definite, we also know that the singular values are equal to the eigenvalues. But looking at the singular values, we're going to get some idea of how much does A distort the unit circle. And we can measure this by its 2 norm. Turns out if we find the largest value such that A vi in its 2 norm, we have an indication of how much A distorts it. And again, since these 2 vectors give us an idea how much distortion is going on, they're going to turn out to be our way we're going to use it. We'll take k unit vectors. If we compute a bunch of those, we can say the 2 norm of A is approximately equal to the maximum over all these different vectors of the 2 norms length of A times vi. And as we increase k, we're going to get better and better approximation to the 2 norm. So effectively, we take the max over all unit length vectors of the norm of A times v. That'll give us the 2 length vector. Now, we only did that for 2 by 2, but matrix norms are not restricted to 2 by 2 matrices. So for an n by n matrix, we're going to say its 2 norm is just equal to its largest singular value, which is true for any number of dimensions. The inverse matrix, A inverse, undoes this action. And if we let the singular values of A inverse be called sigma hats, we know that sigma hat of 1 is 1 over sigma hat of n is 1 over sigma n. And so the largest singular value associated with A inverse is 1 over sigma n, which is 1 over the smallest singular value of the original matrix. And so this is from SVD, which we've already seen. So now we can see that we can take any matrix and we can get its 2 norm, which we got by thinking about it in terms of trying to approximate the geometry of the distortion by just looking at its largest singular value. Now, just as we had other types of norms, we can have that for matrices. So analogous forms of vector norms. So the 1 norm for a matrix is the maximum absolute column sum. The infinity norm for a matrix is the maximum absolute row sum. And there's another norm. We have to be a little careful. We have this thing called the Frobenius norm, which gives a total distortion of A, which is the square root of the sum of its singular values, and which turns out to also be the same, although that's not obvious, to be equal to the square root of the sum of all of its values. So in vectors, the 2 norm was the sum of the square root of the sum of the squares of the elements. In the matrix space, the 2 norm is the largest singular value, and the Euclidean norm is the square root of the sum of the squares of all the elements. The Frobenius norm, they're not the same. So just putting a 2 here doesn't tell you it's the same as in a matrix and vector space, so you have to be a little careful there. So in matrix form, just to make these clear, the sum, the column sum, the first norm, is the maximum of the sum of the absolute value of each element down a column. The Frobenius norm is the square root of the sum of all the elements squared. The infinity norm is the maximum of the sum of the rows. And the spectral norm, sometimes another term for the 2 norm, is called the spectral norm because it comes from the eigenvalues, which is where the spectral comes from, is just the square root of the largest eigenvalue, square root of or just the largest singular value. There's ways of computing those from Octave and MATLAB, so they're just functions called norm. There's another thing called condition number, which we'll talk about in just a second. So just to put these into context, again, you should be able to compute norms. So given the matrix 1, 2, 3, 3, 4, 5, 6, 7, with singular values 10.5, 7.97, and 0.334, the 2 norm is the max of the eigenvalues, that's 10.5, or sorry, the singular values, 10.5. The 1 norm is the max of the sum of each of these columns, so 5 plus 3 plus 1 is 9, 2 plus 4 plus 6 is 12, 3, 5, and 7 is 15, so that gives us the 1 norm is 15. For the infinity norm, we just sum the absolute values across the rows, and we'll get 18. And the Frobenius norm, square root of the sum of all the squares of elements, is 13.2. You can again see if computationally we try and avoid the Frobenius norm, we get all these squarings, it's a lot more expensive. So we tend to do things for matrices using either the 1 norm or the infinity norm because they're cheap. The 2 norm the spectral norm looks like it's cheap, but because we have to compute singular values, there's a lot of work to get there. Matrix norms are real valued functions. They satisfy all the properties of norms we just talked about. So they're greater than 0, they're equal to 0 only if it's equal to 0. They're linear scalar. They satisfy the triangle inequality. And they have one more thing that's useful to know is that the matrix, the norm of a product of matrices is less than or equal to the product of the norms of each of those matrices. So it depends on the computational expense of what we want to do. And what we want to do with them. So the Frobenius norm and 2 norm, even though those are the most expensive, are invariant with respect to orthogonal transforms. So it doesn't matter if I rotate or do anything else, whereas the infinity norm and the 1 norm both change as I rotate my space. Okay, so now let's come back to the broader capability. We're going to bring these two ideas together. We're going to talk about the stability of a method for solving a problem and the stability of a method for solving a problem is basically saying how sensitive is the method to rounding errors that in the solution process. And a method that is guaranteed to be as accurate as the data warrants is said to be stable, otherwise the method is unstable. So if I make a different way of looking at this is a stable algorithm is one where a small perturbation in the input produces a small perturbation in the output, and at least within the scope of where that problem is going to be. And then we can talk about the condition of a problem with respect to the sensitivity of the problem perturbations in the data. So if a problem is ill-conditioned, if a small change in the data causes relatively large change in the solution, otherwise a problem is well-conditioned. So we can talk about stability of algorithms. We talk about conditioning of a problem. As we've already seen, when we start mixing really big and really small numbers, this can lead to ignoring the small numbers, which often limits the conditioning of that particular problem, even when I'm using a stable algorithm. So when we want to talk about how much error we have in our problem, we can do 2 types of what are called error analysis. Error analysis is concerned with establishing whether or not an algorithm is stable for the problem at hand. And so what sort of errors do we have? And a forward error analysis is concerned with how close the solution is to the exact solution. And it turns out that you can do this. It's called forward analysis because you sort of start with the errors at each piece of the equation and work them forward step by step. And it can be a little bit expensive. In a backward error analysis, which is more commonly used today, is concerned with how well the computed solution satisfies the problem to be solved. So we look at the answer and say, how well is that an approximation to what it should be? In a forward analysis, we say, how far is the answer from where it exactly should be? So let's look at a backward error analysis for linear systems now. So if we know that AX equals B, and we also know that we didn't get A exactly. Now, we could actually imagine that we didn't get B exactly, but it doesn't really matter. We're going to combine them all into this formulation. And so we're going to ask the question, if there's a perturbation in A, it's going to affect the solution of X. So we're going to relate, instead of solving AX equals B, we're effectively solving A plus E for some error matrix, X hat equals B. And we can ask then the question, how well do we get, how close is X hat to X? This is an estimate of the backward analysis, and it turns out we can relate that to the forward error analysis if we want by looking at the fact that the norm of X minus X hat divided by the norm of X hat is less than or equal number to the condition number times the norm of E divided by the norm of A. So if we think about the norm of E divided by the norm of A, this is sort of the relative amount of error that shows up in A. Right? Now, if all we had was round-off error and single precision numbers, then the norm of E would be all just numbers that can't be represented in our computer but are close to A. So this would be like something on the order of 10 to the minus 8th, and then it'll depend on what is the norm of A. That times a condition number will tell us how far off our answer can be. So to see where that comes from, we just go back in and we know that we have, this is the solution we're going to be looking at. So we're going to take A times X minus X hat equals E X hat. That's just taking these two equations and combining them, we're subtracting them from each other because they're both equal to B. And that gives us that X minus X hat equals A inverse E X hat, assuming that A is invertible. That gives us X minus X hat divided by X hat less or equal to A inverse times E. And now we're going to define this condition number as the norm of A times the norm of A inverse. And that allows us to then rewrite this as sort of the relative error in representing our matrix times the condition number. And this condition number is going to be what we're going to use to estimate how hard or how well we can solve our various linear systems. To put that into context, let's say I have this matrix, 99, 98, 100, 99. You can see these are not linearly dependent, but they're pretty close to being linearly independent. So the norm in the one norm, because that's the easy one to compute, is 199. The one norm of the inverse matrix is also 199. So our condition number is 199 squared, which is about 4 times 10 to the 4th. And what this means is that if I were to input these numbers in this in less than 4 decimal digits, I'm going to have a problem. So our idea of the condition number is to go back and look at how sensitive is the solution to AU equals B to changes in either A or B. And the reason to see why this is so important is let's go back to the action ellipse, and it describes the geometry. So again, in 2D, if sigma 1 is very large and sigma 2 is very small, we get a very, very elongated ellipse. Okay? And when we go to invert it, we have to then back project the data. And so this distortion is going to amplify any small errors in the solution are going to be amplified when we have to project them back, especially errors in the vertical direction because of the way this ellipse is laid out. Turns out our condition number, although we did it in the one norm in the previous slide, we can do it in any norm. It'll give us similar results. Our 2 norm is, in the 2 norm, that's just the largest singular value divided by the smallest singular value. And that gives us a way of looking at how elongated or distorted is our space. And that limits how much we can do. As a rule of thumb, if your condition number is 10 to the p, then you're going to lose p digits of data out of your computation. So when we talk about the condition number, we have to remember that A transpose A was symmetric and positive definite. And so the condition number is always greater than or equal to 1 because it comes from the singular values. If A is well conditioned, then the condition number will be very close to 1. For example, a rotation matrix has a condition number of 1, and there's no distortion, so its singular values are all 1. But something that is very ill-conditioned will have very, very disparate ones. And clearly the case of singular matrices, smallest singular values are 0, and so they have infinite error in terms of trying to solve that. We can try and solve in the least square sense, but we have to be careful because if I take A transpose A and I try and solve things in the least squared sense, we know that the condition number is actually going to be squared. So it'll reduce our accuracy. So if we go back to solving this A equals B, we want to be careful how we made our matrix, but depending on or what problem we choose to solve, we at least need to understand what our errors are going to be. So as your guideline, again, as I said, if our condition number is on the order of 10 to the k, we're going to lose we're going to lose k digits of accuracy. So if my matrix had a condition number of 10 to the 4th, and you only gave me 2 digits of accuracy in A, I actually have nothing left in my answer. I may be completely wrong. So if the condition number is large, then the solution can't be depended on, and this is really irrespective of round-off error, because just to put the data in the computer, I may have already lost it. So a nil-conditioned matrix is very sensitive to small changes in A or B, and so you need to check that. When you first set up your problem, even though it's expensive to compute the condition number, I strongly recommend if you're working on a new problem for the first time, you go out and check your condition number. Very often your condition number becomes bad because because of the constraints and the way you formulate your problem. You might be able to reformulate it in a way that will make it better. The condition number turns out to be a better measure of singularity than the determinant. The scale and size of it are invariant. So if I look at the condition number of S times my matrix A, that's just going to be equal to my condition number of A. It doesn't change. But obviously we know the determinant changes a lot. So if I take my identity matrix I in 100 dimensions and I multiply it by 0.1, the determinant of I is 1, the condition number of I is 1. But the determinant of J is 10 to the minus 100, and the condition number of J is 1, right? I just have an identity matrix scaled, right? It's an easy to solve problem. So the determinant being small suggests there's a problem with the matrix, but there really isn't, because the scale of J poses no problem in a linear system. The condition number combines a bunch of information to give you a better overall idea of how difficult it's going to be. If we go back to solving overdetermined systems, which I said we might do if we take A transpose A times U is A transpose B. The condition number of A transpose A is just the condition number of A squared. So if A has a high condition number, so if I started with a matrix that was already poorly conditioned, solving it by doing A transpose A, the Gauss transform, is expensive and makes the problem ill-posed. So chapter 13 presented a method called the householder method for solving this. SVD is slightly more expensive than householder, but equally stable, and I like it because, in fact, not only do you get the solution to the least squares problem, you also get the condition number, so you can get a feel for what's going to happen. In fact, last class we introduced this idea of the pseudo-inverse. Often you want to use the pseudo-inverse and set 1 over Wi, where Wi is your singular value, equal to 0, whenever Wi is less than the largest singular value times 10 to the minus eps, where eps is the accuracy at which you input your measured data. Why would I want to do that? Why not just use machine precision? Think about it a second. So if you got data because somebody went out and measured with a ruler a bunch of stuff, that data is inherently inaccurate. And so it's not just the machine precision of accuracy, and that decides what we want to do. We want to say, find me a solution that's within the measured accuracy of whatever input data I had, and use that to drive your solution. And so with SVD, you get that as a very easy solution. You just ignore singular values whose relative size compared to the first singular value is more than that number of digits away, and you'll get an answer as good as your input data, which is really what you want to get out of the system. And as I mentioned, you can always get MATLAB to not only give you norms, but it'll give you condition numbers. And although we talked about the condition number in the spectral sense, the second norms, you can actually compute condition numbers with respect to the P norm or the Frobenius norm or any other norm you want, and you'll get slightly different answers in terms of what those things want to be. One last thing with respect to numeric stability in calculations. Good numerical analysis is difficult, and so until you've taken a few courses in linear algebra and advanced numerical analysis and know how to implement these, please don't implement linear algebra packages. There's a well-known package called LAPACK and a bunch of its brethren. LAPACK is for dense banded linear algebra systems and shared memory computers. It underlies a lot of the libraries you can get. It's free, open source. It's in Fortran, but it's been translated to lots of different languages. It'll give you solutions to systems of equations, linear least squares problems, eigenvalues, singular value problems, generalized versions of these we didn't even talk about, matrix factorization, condition numbers. And maybe for you, the other reason to consider doing it is it has this layer called BLAST for the basic linear algebra subsystem as a portability layer. And on many, many architectures, this has been highly optimized by people who know what they're doing to make it run faster. So don't implement from scratch. Reuse existing packages where a lot of the touchy numerical issues have been handled. So that's it for numerics. Thanks. You should probably make sure you understand all the terminology that's in this lecture. There's a couple of terms I expect you to do. You should be able to work out various basic problems in terms of what will things do in terms of computations with simple floating point numbers, and then be able to also deal with computing norms in both vectors and matrices, and